fact, using a dive light is the only way to compensate for the selective absorption of colors and the reduction of natural light. Lastly, the use of a dive computer is compulsory on the PSS Deep Diver course. The depth itself is a penalizing factor regarding the dive time. A dive computer allows you to make longer dives within the no-deco dive time than if you made the same dive using the dive tables. This is particularly true when making repetitive dives. Regulators. The purpose of a diving regulator is to reduce the high pressure of the breathing mix in the cylinder, variable with time, to ambient pressure, variable with depth. All dive regulators are open circuit, meaning that after taking a breath, the diver exhales the air into the surrounding water. Diving regulators are on demand, meaning that they supply breathing gas only after the diver has demanded it and adjust automatically to the changes in depth. The first models were single stage, meaning the change of pressure occurred in just one stage. Technical evolution has led to the two-stage model, which is easier to breathe from as the final change in pressure occurs right in front of the lips. The function of the first stage of a two-stage regulator is to reduce the high pressure of the breathing mix in the cylinder to an intermediate pressure or hose pressure, which is equal to the ambient pressure plus a predetermined value. The second stage of a two-stage regulator further reduces the intermediate pressure to the ambient pressure so we can breathe effortlessly. The first stage. There are two types of first stages: diaphragm and piston. The main difference is that the pressure-reducing mechanism in the diaphragm type, contrary to the piston type, works in a dry environment. In the piston type first stage, the ambient pressure is transmitted to the pressure-reducing mechanism directly by the water that enters it. Instead, in the diaphragm type, the ambient pressure is transmitted via the force exerted on the diaphragm. This is why diaphragm-type first stages are preferable for dives where there is a lot of silt suspension in the water. The dirty water remains outside the pressure-reducing device and therefore cannot damage the mechanism or affect its working properly. Downstream and upstream valves. The passage of breathing mix from the first to the second stage of a regulator occurs through the opening of a valve. This valve can be either downstream or upstream, depending on the direction the valve opens in respect to the flow. A valve is downstream when it opens in the same direction as the flow. If the valve opens in the opposite direction to the flow, it is said to be upstream. The advantage of a downstream valve is that if the pressure upstream is higher than normal, the valve will open and allow gas to flow out. This is why all safety valves are of the downstream type. The disadvantage is that the force generated by the thrust of high pressure on the area of the valve head changes with the variation of pressure in the cylinder, thus affecting its performance. Balanced valves arise from this fact. Balanced valves. Upstream of every valve, there is an imbalance of forces due to the reduction of pressure as the diver consumes the breathing gas. Balanced valves were designed to reduce the effort of opening the valve, meaning in such a way so that the pressure acting on the valve head is counterbalanced by an identical force that acts in the opposite direction. A special balance chamber ensures that the same pressure that there is upstream of the valve acts on an area of the piston the same as that for the passage of the breathing mix. There are two ways of connecting the balance chamber: using an external or an internal feed line, which is usually the method used in regulators. In this way, with variations to the high pressure, the effort of opening remains practically the same and is dependent on a single spring. When the two areas on which the axial forces act are the same, the valve is perfectly balanced. If they are different, the effort of opening varies with the changes in pressure upstream. For example, if the head of the valve stem has a smaller area than that for the passage of the breathing gas, the valve is partially balanced. In the opposite situation, the valve is overbalanced and the effort of opening is reduced as the pressure upstream fails. The second stage. In regards to how it functions, the second stage of the regulator is much less complex than the first stage. It is just a simple pressure regulator on demand, which functions with the difference in constant pressure, meaning that it brings the breathing mix from the intermediate pressure to the ambient pressure, making a change equal to a predetermined pressure. The heart of the second stage is the downstream valve. The seal of the downstream valve is created by a seal mounted on the piston, which is pushed by a spring against the seat. By breathing, we lower a membrane, which activates a lever which then pushes the piston away from the seat and allows the breathing gas to pass through. Once inhalation has stopped, the membrane returns in position and the spring pushes the piston back against the seat, closing the flow of breathing gas. Balanced valves can also be used in the second stage. Using a balanced valve means that the force of the spring can be greatly reduced and consequently breathing requires less initial effort. As well as the balancing of the piston, with time a second stage with an adjustable flow, which acts on the compression of the spring, has also proven useful. If the calibration is optimal, on the surface the second stage of the regulator should go into free flow with the adjusting knob unscrewed and stop when the knob is almost completely closed. In this way, as you descend, you can unscrew the knob and reduce inspiratory resistance to as little as possible. As you ascend, you can begin closing the knob to stop the tendency that the second stage has to free flow. We speak about initial respiratory force to indicate the effort needed to open the valve of the second stage. The subsequent force, inspiratory force, needed to keep the valve open is always less than the initial effort required, also due to the laminar airflow which opposes the closure of the piston. The fluid dynamic effect Venturi, or a dragging or ejector effect, is much more effective. By directing the flow of air into the mouthpiece, we obtain downstream a pressure just a little greater than the ambient pressure, and upstream, in the casing of the second stage, a slight depression. This depression helps to keep the membrane lowered. In this way, the inspiratory effort can be reduced to zero. With some of the early Venturi models, any slight accidental maneuver was enough to trigger a free flow. To reduce this effect, manufacturers invented depression limiters, which introduced obstacles along the route of the gas flow. An alternative solution is to use an external bypass tube. In practice, the air passes from the second stage valve directly to the mouthpiece by means of a small auxiliary bypass tube, keeping the chamber of the second stage almost completely in depression and greatly reducing the respiratory effort. Still, with the purpose of reducing the respiratory effort to the minimum, an element commonly used in mechanics has been applied to regulators: servo assistance, meaning a mechanism that is able to carry out a given function after receiving a particular command. With the servo-assisted second stage, the depression created by our inspiration uses the same air at intermediate pressure to open the valve. In simple terms, we can say that instead of opening the valve of the second stage, our initial respiratory effort serves to open a very small valve. In this way, the initial effort is reduced to as little as possible. Emergency air sources. One of the reasons why the buddy system is important is that it avoids having to carry around a reserve of breathing gas in case of an emergency. In case of problems, you can share your supply with your buddy. On the PSS Open Water Diver course, you learned that there are various types of emergency air sources. These may be dependent on your buddy, octopus system, or integrated into your BC, or completely independent, small auxiliary cylinder. A valid system when deep diving is a second regulator, completely separate from the main one. In this case, you will need a cylinder with a double outlet.